Hi, this is Ana Doblas, and in this video we're gonna solve 4 different multi-choice questions about wave optics. So the first one is about they give us the equation of a light wave, and they ask us about the refractive index. So we know that in the general form we can say that the wave function follows a sinusoidal that is periodic with respect to time. Let me make it kind of backwards just in terms of the sign, but here we're gonna say your wave number x minus r wave field changing periodically with the time and an additional phase. So if we compare with the previous equation, we know that our wave number is 1.5708 multiplied with 10 minus 7. This is our wave number. And then our angular frequency is 3.1416 multiplied 10, 15. Alright, so the velocity, which is what we're gonna find out, this is gonna be our wavelength multiplied with our frequency, but we know that the wave number is 2 pi over the wavelength, so that means that the wavelength is 2 pi over k, and now our angular frequency is 2 pi our frequency, so our frequency is omega over 2 pi. So that means that the wavelength is going to be 2 pi over our wave number, and the frequency is the angular frequency over 2 pi. So as you can see, the 2 pi's cancel each other, so we're going to have here our angular frequency out over our wave number. So when we think about our refractive index, this is the speed of the light over the velocity, right? But now we can put here the velocity over the angular frequency over your wave number. So we have the wave number over the angular frequency multiplied by c. So now is the moment that we can plug the values. So 1.5708 multiplies 10 power 7 excuse me, over 3.1416 multiplied 10, 15, and then the frequency is the universal constant 3 multiplied by 10 power. So that means that our refractive index is 1.5, which is gonna be our solution, our C option of the problem. Alright, so the second problem of this video is about approximating a spherical wave as a paraboloidal wave. So we know from the video class that a spherical wave with radius a can be approximated as a paraboloidal wave if a power 4 is so much smaller than 8 times the multiplication of the wavelength and the axial distance from power of cubic. So remember, 8 is the radius and this is gonna be the axial distance. So that much smaller means at least one order of magnitude. So our radius to the power of 4 needs to be smaller or equal than 8 times lambda c cubic divided 10. So, and that 10 is because there is at least one order of magnitude. So the radius is smaller or equal to the 4th root of 8 lambda c cubic over 10. So now we put all the values that we already have here. So A, it's blue color, 488. We put everything in meters. 2 power to the third over 10, and this is 42,038 millimeters. So the maximum value of our radius is gonna be 42.038, and that means that this is gonna be the answer. Alright, so question number 11, I think it's a fun question. They say that we are building the Young experiment, right? So that means that we have here our 2 pinhole or 2 slits separated by a distance 2a, and then we are far away. We are observing the interference fringes, and we know that if this is the Young experiment, then we're gonna have here 2 times the initial intensity of each slit, 1 plus the cosine of 2 pi lambda 2a over d x, assuming that this is gonna be on our x direction, right? And they are saying that the separation between 2 consecutive maximum, but we already know that it's gonna be the same for 2 consecutive maximums or 2 consecutive minimums, is lambda d over 2a. And the problem tells us that this is already 25.3 millimeters. So the problem is telling us also that our distance d, this is gonna be 10 meters from the slit to the screen, and then that 2a is gonna be 0.25 millimeters. So now the problem is asking us that they are telling us that we are blind color, we don't remember what was the wavelength that we used, so we need to estimate the wavelength. Alright, so we have the separation. So we know the separation between the maximum, we know the distance, and then we know the separation. We can separate the wavelength, or we can write the wavelength as 2a over d multiplied by the separation between the 2 maxima. So this is gonna be 0.25. We are putting everything in millimeters, and then the powers of 3, as I was saying, everything is gonna be in millimeters, and then 25.3 millimeters. So that means that this is 632.5 power 10 minus 6 millimeters. So lambda is equal to 632.5 nanometers. And that means that our correct solution is gonna be the A option, red color. The laser was red. Alright, so the last problem of this video, it's also relating with the superposition, but now we have the superposition of 2 coherent wave with the same initial intensity. So this is gonna be our final is gonna be 2 times the initial or the input, the incident intensity of each wave, and then 1 plus the cosine of the phase difference between both waves. So phi1 minus phi2, this is gonna be phase difference between both waves. So the problem tells us that the phase difference is already known and it's 35 degrees. So our resultant intensity is going to be 2 times the initial one, 1 plus cosine of 35 degrees. So this is going to be 3 times 63.8 the input. So when we see this solution on the solution given, that means that that's going to be the first option. The resultant intensity is around 3.6, the initial one. So I hope that these problems examples help you to solve the rest of the multi-choice questions. Thank you.